see here. Okay, so hello everyone. We are pleased to welcome back Dr. Jeffrey Fung, who got his PhD and undergraduate degrees here at the University of Toronto. He got his PhD working with Pavel Armadowitz. I'm sorry if I mispronounced that name. After getting his PhD here, he went off first to Berkeley, then to the IAS, and now he's going to be a professor actually at Clemson University. So we're very pleased to welcome back Dr. Jeffrey Fung, and he's an expert on numerical simulations of protoplanetary disks and planet-forming environments in general. And today what he's going to talk about is a really neat code that sounds like he's developed. So thank you again, Jeffrey, for coming here, and we're pleased to welcome you back.
Thanks for inviting me. It's nice to be virtually back, but also not nice to be not actually back. Let's just get right into it. I want to talk about something today that is quite numerical. I hope that's okay. I've been warned that it's not a good thing to put too many equations in a slide, but I will have a lot. So just warning. So just a quick outline of what I'm going to be talking about. The first two parts are both about numerical algorithms. First is related to reconstruction in finite volume methods. We have developed a new way of reconstruction. We call it the piecewise exponential method. We'll get into what that is later. And then we'll talk about dust integration, issues with calculating gas drag correctly. And we have a new method, a very simple modification, but improves its accuracy significantly. And the method is called the Staggered Semi-Analytic method. And all of these things are incorporated into my two-fluid gas and dust hydrocode called Penguin. So in the end, I will talk a bit about what I'm using this code for. And one of the topics is studying how planets shepherd dust rings in gaseous disks. So let's just so for the next few slides, I'm just going to explain what reconstruction is. So if you already know, if you just mute me. So the first thing we want to do is here we want to solve Euler equations, and a finite volume method means that we divide the domain into volume elements, and then we evolve it via Green's theorem that you can just calculate the fluxes across interfaces, then you can evolve it in time. So these are just the usual equations, conservation of mass, momentum, energy. So how that works, I have a schematic drawing here. Imagine we have a 1D grid of fluid with 3 cells. So in each cell, you have the cell average value of your conserved quantity, let's say its density. Then you start with this and you only have the cell average value, but then you try to reconstruct the underlying continuous profile that these average values are supposed to represent. Of course, to do this, you need information from neighboring cells. So in here, some reconstruction is done. There's some approximation to what the underlying continuous profile might look like. Then you want to compute the flux. So let's say the flow is toward the right direction, then you can just go ahead and integrate these reconstructed curve over the direction that you want to have material moved over the neighboring cell, then you get your flux. So pretty straightforward. One idea here is that what we call the courant number. So the flux here is again this reconstructed density, which is you take the average of, or you just you integrate over your reconstructed function, and you take the average of that. That gives you sort of a reconstructed value of your conserved quantity, and you multiply by the speed that you're wanting to travel to the right, then you get the flux. So this distance times delta t, which is the time step, divided by the size of your cell. This is a dimensionless number. It is a measurement of the time step. It's the courant number. I'm going to get back to this number. It's a very important concept. So you might notice that when I drew these curves, these are not actual reconstructions. I just drew this, but I on purposely drew over here such that the curve on this left side rises above the curve on this right side. And this happens very often in reconstruction because when you reconstruct your underlying continuous profile, each cell uses different amount of information. So this cell, for example, only knows these neighboring cells, and this cell knows these neighboring cells. So they don't know what is the reconstructed profile in its neighboring cells. Sometimes it's going to overshoot. So this is a problem because now you have some sort of artificial extremum created over here, even though the cell average density don't suggest that there should be anything like that here. So this is a case where your total variation in your profile is not conserved. So to fix this, there are these what we call the total variation diminishing algorithms, which is basically you take your flux with using some higher order way of approximating the background profile. So something like piecewise linear, where these curves would just be lines, or piecewise parabolic, where these things would look like parabolas. And then you do a linear combination of that with something that would guarantee that your total variation is diminishing, like piecewise constant, which is just taking the cell average value as your piecewise function. So clearly, in this case, you will never create artificial bumps like this. So if you lean too much towards this side, using more of the piecewise constant method, then you tend to produce more diffusive codes. If you lean more towards this side, then your code is more accurate. But at the same time, this kind of thing would happen more frequently, and you would end up with artificial oscillations in your code. So usually this parameter that you use to determine which one you want to use is a measurement of how discontinuous the profile is. And there are so very, very many different ways to compute this function. It's usually referred to as a flux limiter or slope limiter. And there are so many of them. If you just search, flux limiter on Wikipedia, you're going to get tens of them. And there are even more in the literature. One way or another, you either get more accurate solution or more diffuse or more oscillatory solutions. So there's no best way. And this is kind of a problem because in order to choose the best algorithm, you need to know your answer. But then if you know the answer, you don't need to simulate it anymore. So this is one thing that we're going to address. So to begin, just a quick summary of how finite volume methods work. So step one, you have to estimate your boundary values. So that's when you hear a code and they say a code has spatial order of something, that's exactly what they're referring to over here. If you approximate your boundary values in the second order way, then your code has a spatial order second order. If you do it in the fifth order, let's say for example, then your code has a spatial order of fifth order. So after you have your boundaries, then you fit a curve through these 2 points, and there's only one condition, is that it has to conserve the cell average. So quickly, one very common way of doing this is the piecewise linear method. So you just get 2 points and you fit a line through it. This line is basically determined by a second order slope. That is the difference between the front and back cell. Very simple, very common. Many codes, especially in the astronomical community, uses this method. Another way that is a bit more sophisticated and complicated and computationally intensive is piecewise parabolic method, PPM. So PPM uses a 5-point stencil, require even more information, and then you use all this information to fit quartic interpolation to get the boundary values. So you have two points, and now you can fit a parabola to them. So now that gets to PEM, so the piecewise exponential method. So what is that? Now, first consider that we have the same setup, same amount of information that you would use for PLM. What is the highest accuracy boundary values you can use when you have 3 points? PLM is second order, but with this amount of information, we can actually get a third order approximation to the boundary values. So this is, for example, one way. This is the special case where the cells has same width. There is a more complicated way of doing this when the cells are not uniform, but essentially this is the idea. So you have now third order boundaries, but you can't fit a line for it anymore because if you do, it's not going to conserve. In general, it's not going to conserve the cell average. So you need something that has more free parameters to fit through these 2 points. You could fit a parabola, but then generally the parabola may not be monotonic. So for example, to get from this point to this point, maybe the curve is going to look like this, some sort of bump. So when that happens, things have to get adjusted, and then you probably end up with boundaries that have to be shifted from these third order points. So the piecewise exponential method looks almost exactly like the piecewise linear method, but you take so this is what the reconstructed function would look like for PLM. These are the boundary values front and back, and the exponential method, you just take exactly that, and then you add an exponent to your spatial parameter to this current number. So you can do that, and then there is actually a second way of doing it with this mirror image. You just flip left and right, then you get a second way of doing this. You want to make sure that your solution will be the same whether you get a mirror image or not. So you have to choose between one of these two. These exponents, if you just do the simple algebra, you find out that in order for this equation to have an integral that conserves the cell average, these exponents have rather simple expression. It's just looks like this. And then the leftward and the rightward exponents are just inverses of each other. So one is always going to be larger than one, and the other is always going to be smaller than one. So we have to choose one of these two, and we always choose the sharp solution where you have a larger eta. So the exponent, for example, eta r is larger than 1, we will use this expression. If eta l is larger than 1, we will use this expression. So what this actually looks like is this. So here, the dotted line here is the actual background profile, the actual profile of the whatever this is. Let's say it's density, and then the gray is the cell average. If you take this and put it into 5 cells, and then these curves are the reconstructed profiles, with green being PLM, blue is PDM, and red is PEM. So in the limit, when this is more or less smooth, so when this gray bar is sort of in the center, that's the limit where PEM would give you an eta, the exponential that is about 1. So it's basically exactly the same as PLM. But then when you have a sharp variation in your profile, see that PEM tries to bend very sharply to fit this sharp jump in your profile. So I think looking at this, I think the expectation is that PEM is going to produce better results when you have discontinuities in the solution, which your test then now showed. So one important question here is now you put an exponent into your function. What is the order of the schema if you do that? So this is not the spatial order now. This is the order in time. because when you integrate through your cell, that's a finite current number, and the current number is just dimensionless measurement of your time step. So given the time step, you're going to integrate into your function, and it's going to be an exponential function. So what kind of order is that? So to do that, you can take the expression for what you do if you integrate through the PEM function and just expand it in the limit where eta minus 1 is very small, or eta is very close to 1, basically when your flow is close to smooth. So this is the expansion. You have terms of order eta minus 1. And eta minus 1, if you just look at what it is a first order approximation to this kind of thing, which is as the second order derivative of your background divided by the first order derivative times some sort of number. So basically, something that looks like this, eta minus 1 times the slope is an approximation to the second order derivative of the solution. So we can multiply it out and compare it term by term to the Taylor series. Here's the first boundary term. We know that we approximate this to third order. This is the first order term. This is an approximation to the slope. This is a second order approximation to the slope. And then over here, this thing here, as I showed before, is a first order approximation to the second derivative. So that part is matching, but then the front coefficient is wrong in this case. The front coefficient in the Taylor series, this should be eta squared, c squared divided by 6, but now instead I have this weird thing. So in time, PEM is second order because the Taylor series basically cut off here. This part is an error. So if you compare that to, for example, PLM just don't have this third term. So similar to PLM, PEM is second order. But then this front coefficient is useful because it gives us some idea of how large the error is versus what would happen if you just don't have this third term at all. So you can see that if I just plot what this looks like as a function of the current number, they of course have the correct asymptotic value at current number of 0 is 0, but then once you go to finite current number, it rises a lot more steeply than just c squared. So we're going to examine this behavior as well. So to show what the convergence of PEM is, so we do a very simple 1D test that is basically a sine wave, very low amplitude, a linear sine wave, just propagating in a periodic boundaries. Then I'm going to plot the L2 error coming out from the numerical solution. So here we see the error as a function of resolution. So this is how many cells per wavelength of the sine wave. And then this dotted line here shows second order convergence. So when the current number chosen is quite small, so in this case 5%, we get somewhat expected result that PEM converges in a way that is steeper than second order because the boundary values are approximated to third order. Whereas PLM, you see, very well behaved, is exactly second order. And then PPM and PEM are somewhat steeper. And then we, again, as expected, when we choose a current number that is 0.5, PEM is still second order, but there's a sort of a jump, a transition, where the error starts going higher, and then again it converges second order. So this is the behavior of PLM PEM when the solution is relatively smooth. That's because if I go back to here, eta -1, where this error originates, is scaling to this kind of thing. And this C here depends on the resolution. C here, again, is the current number, which is divided by the cell size. So when your cell size is smaller and smaller, when the cell size is smaller and smaller, so higher and higher resolution, the error in the third term dominates. And then here we look at how it changes with resolution, with current number at different resolutions. So when the resolution is low, again that third term is reduced. So PEM just performs well across the board regardless. But then when you go to higher resolution, you start having this this rise in error as you as the current number is larger. Becomes larger. So if any of you in the audience does this kind of simulation, you would know that usually we choose current numbers that are something like current limits that are something like 0.5. So it would seem like this somewhere over here is most relevant. But at the same time, I should remind you that it's not a number that you choose, it's a limit that you choose, meaning that it only applies to the cell with the fastest speed in your simulation grid. So actually, if you choose a current limit of 0.5, your entire grid runs with a current number that is less than 0.5, and sometimes less than 0.5 by a lot, depending on how much speed variations there are in your code. So I think this other limit where you have the small current number is still quite relevant. But regardless, all three methods clearly converges quite well. And even in the case where you have the largest discrepancy, the error only differs by about order of unity, maybe a factor of 5 at most. So numerical diffusion, this is one thing that PEM really is designed to tackle. We want to approximate sharp transitions very well. So let's see if it's doing that. So this is test. It's not a hydro test. It's just an reflection test. You take a triangle, you take a top hat, and you take a Gaussian, and you spin it. These are periodic boundaries. You just spin it around and around and around, and just see how these shapes are going to get diffused out. So this is the simulation. PLM, clearly the most diffusive. Again, like I said before, PLM and PPM depends on the limiter that you choose. So this limiter that I chose for PLM, the 109 central, is one of the least diffusive limiter for PLM, but still, after 1,000 cycles, you see that the original shapes are basically completely eroded. PPM is doing well. PEM is doing almost equally well. Oh, yeah. So having code that is low in diffusivity is great, but then, like I said before, when you have low diffusivity, you tend to produce more spurious oscillations. So let's check that by having a test with very strong shocks. So this is famously known as the two interacting blast wave problem. Looks like this. You have high pressure on these edges, and then they just produce a blast that propagates inward, and they're going to collide and create a rather complicated structure. Here I'm actually plotting 3 solutions, each from one of these reconstruction methods, but they are almost exactly on top of each other, so you can't see. So we can assume it. So we're going to look at 3 particular locations. One is here. This is not a shock. This particular place here, this jump here, is a contact discontinuity. So over here we can see the spread from each is supposed to be infinitely sharp, but of course you don't get that in your numerical solution. And PLM again is the most diffusive. PPM and PEM are doing better. In this case, PPM is doing slightly better than PEM. So over here, this one is an actual shock. It's a rather strong shock. And you see that PLM has these spurious oscillations coming off behind the shock. We call these push-shock oscillations. And then PPM is much better. It doesn't have this huge initial spike, but you can still see quite obviously that there is this wave coming off of it. PEM has a strong spike initially, almost the same as PLM, but then right after it's gone. So this is much more stable than both PLM and PPM. Again, these results depend on the limiter that you use. One can choose a limiter that would make these two, PLM and PPM, less oscillatory, but then that would also make them more diffusive. So there's another shock, sort of a similar story. PEM has a relatively stable profile. PLM is noticeably more diffusive. This shock front is spread out a little bit more. And then PPM has almost a shock front as PEM, but again, you see a bit of a hint of some oscillations. So this is the summary of what PEM is. It is a reconstruction method that is spread order in space. It uses a short stencil, just one neighboring cell on each side, just like PLM. So this it simplifies calculation, simplifies data transfer, and then no limiter. So you don't have to worry about limiter at all. You don't have to worry about what to choose. Numerical diffusivity is quite good because it's able to model sharp discontinuities quite well. But even so, it's quite stable at shocks, with, even without any limiter. And then errors are good, except when you have a very well-resolved smooth flow and your time step is large. In that case, it is performing not as well as PLM by at most a factor of something like 5. Okay, so I'm going to move on to the next topic, which is dust integration, if there's any question. Okay, so
did you try to work out like a metric of, right? You've got the larger error if you lose a large time step,
yeah.
but of course your code's going to run faster if you run a larger time step. So there's going to be a trade-off there. Although, as you pointed out, a lot of the cells are not going to have that problem.
Yeah.
Maybe try to quantify, sort of where's the best place to be in terms of step size and so forth.
Because in general, most of your grid would not have that problem. I would say just pick 0.5. It's not really a big deal. And usually, especially it's like most questions, it's problem dependent. Say, for example, if you have a problem that has strong shocks moving around, then the shock is where you're going to actually reach your current limit that you set in the code. And that is not a smooth flow. So PEM would just be totally fine with it. So in general, I think it's just, unless you are doing a problem that is just generally subsonic, then you, then I think, I cannot say for sure what kind of current number you might want to choose the best. But if your problem would end up with shocks running around, then basically this problem of having a larger error when the flow is smooth is not going to be a problem for you.
So Jeffrey, I have a related question, but it's really stupid, unlike norms. So why is Courant number smaller? You get larger error?
Oh, that's just, it's a good question. It's just because you take more steps to get to the time that I measure this error. So this is not the error per step, this is the error after a particular time.
Yeah.
So it's just a lot more accumulation of error.
Just to round off.
Yeah.
except some of your PEMs don't have that
It's
problem.
not round off. It's just accumulation of error. Round off will have a different scale length. This is just every step you have some amount of error and you just add it up. So PEM has this weird behavior that it has a very steep rise in a particular term in the error when your current number is larger. So it sort of overwhelmed that trend.
Okay. So this probably is well known in the field, but so this is the graph that shows you should take an optimum Coulomb number, which is not very small. Is that right? This is what if your Coulomb number is small, you often ends up with worse.
Yeah. I think for most methods, something like 0.5 is good. If you go to larger than 0.5, for some problems, it's going to be unstable. For this particular problem, it's not.
Okay,
and then
just this problem.
Yeah, and then the PEM, picking 0.5 seems bad here, but that only is true if you are solving a rather boring problem.
Okay, all right, thanks.
There's another effect here, and I think this particular shape that you're getting is a feature of the problem that you chose. So there's an effect. So in your problem, there's only one relevant velocity. It's just the speed of sound. And when you have just a single velocity, then you get this effect called the magic time step, right? Because when the current number is equal to unity, then you don't get any errors, right? Because at every step, the wave moves at exactly one cell.
Yep.
But if you had a problem that involves, so right, in a one-dimensional problem, you have three different velocities, right? You have the fluid velocity and two sound waves. If you had a problem that involved more than a single relevant velocity, then you wouldn't get this effect because you could never choose a single value. Then the magic time step effect would disappear.
Yeah, I agree. So if there's a different problem, then it's not going to fall so steeply towards large current number. Yep. Okay. So I want to talk about integrating dust motion. This is.
Could I just interrupt one more time? So this is only a 3 orders. I mean, it's only a stencil 3 cells.
Only 3 cells. Yeah.
Yeah. So it's going to be faster.
It is.
There's going to be fewer operations, right?
It is. Yeah.
Coil.
It is almost exactly the same speed as PLM with one caveat. It's that you have to compute a power to a non-integer, which is relatively
which is expensive.
Slow. Yeah. So there are things to do numerically to make this faster, but it will be slower than PLM just because of that particular step. Okay. So for dust, so the question that I want to deal with here is extremely simple. If we have dust with velocity v, then the acceleration, you can write it very simply like this. You have a force that is just everything other than gas drag. And then you have the gas drag, which is the velocity difference between the gas and the dust, divided by a thing called stopping time. This is one way to write drag equations. And I'm going to even simplify this further by considering only linear drag. So that's a stopping time that is independent of speed. So this, for example, the subsonic Epstein regime stopping time looks like this, as is the grain size, density of the grain, density of the gas, and mean thermal speed. Or the Stokes drag, similar things, but over here you have the kinematic viscosity. So,
quick question.
Yes.
Are you treating the dust particles as particles or as a fluid?
I'm going to discuss right now in the framework of a particle, but the fluid thing will come up later too. So a problem that is well known is when the stopping time is extremely short, so the drag is very strong. And particular is if your stopping time is shorter than your time step, then whatever order of the method they're using, it has no meaning because the error would scale as delta t over ts, which is larger than 1 to the power of your order, and it's divergent. So to fix this, you have to have the right limit. There are two most common ways of dealing with this. One is the implicit method, which is just the generic implicit method applied to this problem. And you're going to end up advancing your speed in time step in a way that looks like this, using, so tau here is just the time step divided by stopping time. Or a slightly better way is the semi-analytic method. So what's special about this is that this is actually the exact analytic solution if this gas speed and the stopping time and the external forces are all constant in time. But either way, you can see that with these kind of limits, when stopping time is extremely small, you're going to end up with your v I plus 1, your speed in the next time step. You're going to end up setting it equal to the terminal velocity equal to this, regardless of what step size you use. So you get this number if you choose delta t equals to 1 or a million. So this is clearly a problem because you have these values that are basically chosen at the beginning of the step. So meaning that you just set your speed to the terminal velocity at the beginning of the step, regardless of what step size. This is always going to be first order. So the semi-analytic method, the staggered semi-analytic method, looks like this. We start with a position x0 and then a speed v0 at the beginning of the step. We're going to push forward the position using this initial speed, and then we're going to take this position, but still using the speed from the beginning. So this is a staggered step, and compute the forces, computing the gas velocity, and push it to a mid-time step. And then you take that speed and you recompute your forces, and then you push it all the way through to the end of the step. And then finally take that speed and evolve your position to the end of the step. So in this way, you can see that in the limit of a terminal velocity, you're going to end up with a terminal velocity at the mid-time step. So now your terminal velocity is time dependent. So that's very good. And of course, if this looks very simple to you, and if it even looks familiar to you, you should, because this is really just a drift kick drift leapfrog scheme with a staggered step inserted in the middle. So extremely simple fix, really straightforward to implement. And so such a simple fix, what can it do? Well, let's do a test on it. So I'm going to test it with using by computing the radial drift of dust grains. So dust in a disk, they lose angular momentum and drift inward from gas drag. And that drift speed is a function of the Stokes number. So the Stokes number here is defined as the stopping time divided by their orbital frequency inverse. So that is the dynamical time of the orbit. So a good algorithm should, of course, get the speed right. We're going to compare SSA with a bunch of other algorithms and show the results with a range of Stokes number and time steps. So the other algorithms that I'm comparing with is what we call SA1, that is the first order semi-analytic method, the exact same thing that I just showed you 2 slides ago. Or the second order implicit method, which is implicit but second order. Or a variant of the Radial method, which is a second order symplectic method. So the strong drag regime where your time step is larger than the stopping time are over here on this plot when the time step is this, or over here on this plot when the time step is that. So black curves are the results from SSA, and you can see that all these other codes, other algorithms, regardless of method, they all end up giving you almost the same answer. And again, that's because they all just give you the terminal velocity at the beginning of the step, no matter what you do. But SSA get orders of magnitude improvement. And of course, SSA basically seamlessly transitions into a drift, kick, drift, leapfrog scheme. So it works very well when the dust is not well coupled either. So I think this is super simple, very accurate. Everyone should do it all the time. If you're integrating dust particles, just add a step in there. It's going to make everything much better. And then a second test, and this time we are treating dust as a field of pressureless fluid. So of course now then the dust is associated with a resolution. So this is a dust in a disk. Resolution is shown here. The first number is number of cells in the radial direction. The second number is number of cells in the azimuthal direction. SA again here is just the first order semi-analytic method. And here we are modeling particles with dust number 0.1 and they're drifting inwards. We're measuring again the error, the relative error in the radial speed. And because this is a grid, so we have to compute fluxes through reconstruction. So we are using the PEM method and velocities are evolved using SSA. Then you get this kind of drift speeds error. And clearly we have orders of magnitude improvement, faster convergence. Pretty simple fix to get pretty good results.
So what's the magic thing at 1.5 radii?
Oh, it's just the error flip sign. I'm plotting the absolute value of the error, but the error flip sign over there.
Yeah, no, but I mean, I'm thinking it goes through 0. And there must be some physics in there, or not physics. It's due to your algorithm. But
I'm not sure. That's a good question. Is there something particularly important? It's possible that because the time step of course is equal throughout the entire grid. So I think maybe around here the time step becomes proportional, similar to the stopping time.
Yeah, so it's similar to the magic time step that Almog was discussing earlier, likely. Yeah, so if you have multiple particles, it's not going to work. You can't do it that way. That's fine.
Yep.
And there's this tradition in planetary dynamics. Jack Wisdom used to pick his time step this way often, looking for these things, right?
Yeah.
Yeah.
That's true. That's true. Okay, so you might ask why am I modeling dust as a field of pressureless fluid? Seems like a confusing thing to do. And that's because I want to put it into a hydrocode. So Penguin is a hydrocode that I developed when I was still a grad student in Toronto. It retains the name, but the content has changed a lot since. So here's a brief description of what's in there. I spent the last few months in lockdown writing this code. So it's relatively new. It has reconstruction methods in all the ways that I've already shown you. The Riemann solver, there are several different choices you can choose. You can use the exact solver with a Lagrangian remap formalism, or you can do it in Eulerian frame with several different, also pretty simple Riemann solvers. Fast orbital advection is included so that we can compute disks very quickly. And we have a dust solver, like I just showed you, with approximation with SSA, and everything is done on GPU. One thing about SSA with two fluids is that you need the mid-time step information in order to do the stagger step. So with two fluid, it becomes a bit of a dance. But the general idea is when you compute the flux, which I call evolution in X, but in a grid that translates to computing fluxes. So when you compute the flux, the velocity has to be a half a time step ahead. And when you evolve your velocity, every other quantity, for example, here, when you try to push forward your velocity in the gas, everything else has to be half a time step ahead. So what am I doing with this code? I'm looking into dust rings in protoplanetary disks. So dust rings seems to be a prominent feature in all disks. In my opinion, they are either unresolved or they have rings. It seems like there's no exceptions. And oftenly interpreted as dust trapped at pressure maximum sandwiched by two planets, one on each side, like here, 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 here.
Quick question, Jeffrey.
Go ahead.
Could you look at the previous figures really quick? So do you think also that the innermost regions of protoplanetary disks also should have these beautiful dust rings as well, and they're just unresolved?
Oh, I don't know, but I would not be surprised at all if that's true.
Okay.
Yeah, some of the better resolved one now show the rings inside 10AU.
Exactly.
But
Yeah, there are some.
even look at AS209 there. You can see hints of more rings inside, right?
Yeah.
Yep. Yep. TW Hydra has a ring very close in. So pressure bumps are nice, but problematic at the same time because they are unstable to the Rossby-Wave instability. And that tends to happen if they are narrow. And by narrow, I mean the width of the bump is about a scale height or less. So a typical scale height at this kind of distances, and this is something like 10% of the radius, which happens to be quite similar to the ring widths observed. So this is what happens this is what would happen, if you have a bump here that has a width of something like 2 scale heights, it turns into a vortex. Sometimes it's not a problem because simulations have shown that this kind of vortices can be suppressed if you have an alpha viscosity that is larger than something like 10 to the minus 3. I don't like this idea because I think gas in protoplanetary disks are not viscous. They may be turbulent though, but even if they are turbulent, the amount of turbulence that's been observed seem relatively low. So for example, HL tau here is one of the most robust measurements to date, measuring the amount of dust settling in the disk. And the alpha inferred from that is about 3 times 10 to the minus 4. And then in some other disks, for example, HD 163296, turbulence was not measured. They looked at it and there was no evidence of turbulence. And the upper limit here would correspond to an alpha of a few times 10 to the minus 3. So I'm proposing 2 ways of killing vortices. One is by cooling. So if you look at a vortex core, the geostrophic balance is between pressure and Coriolis force. And I'm going to write here also the centrifugal force, although normally you wouldn't think this matters. If you form a vortex in an adiabatic way, then of course the center is hot because it has high pressure. And then you cool it down. Once you cool it down, the Coriolis force is going to shrink the vortex and reheating the vortex. But once that happens, due to conservation of angular momentum, the vortex has to spin up. So cooling leads to a smaller vortex with a faster spin. And that actually leads to the centrifugal force starting to overtake the Coriolis force. And eventually, at some point, it's going to disperse the vortex. So we have measured this in our simulation. The decay rate when the vortex dies the fastest is something like several hundred orbits. So you see that this decay rate has a function, roughly speaking, a function of this comparison between 2 time scales, which is the cooling time and the turnover time of the vortex, which is something like the dynamical time of the vortex. So the peak decay happens when these 2 time scales are most comparable. If cooling is too fast, then the vortex is formed isothermal, so cooling doesn't do anything. Or if the cooling is very long, then of course there's no cooling and doesn't do anything either. So the second way to destroy vortices is well known already. So that's when you stick in more dust into the vortex. The dust doesn't like going around in the vortex. So the back reaction from the drag is going to slowly dissipate the vortex. So in some existing simulations, the people have found that when the dust to gas ratio is above 10%, vortices don't live longer than 100 orbits. So this of course works, but depends on the Stokes number. So Stokes number, grains with Stokes number about 1 are most easily trapped, and so you get more concentration of that. If you're far away from this, then again, it would not work as well.
How does this work? Why does the dust feedback remove the vorticity?
I don't think it removes the vorticity. It's a good question. I don't know exactly how it goes, but I don't think it removes the vorticity. It just shears away the vortex. So in here, this plot here is vorticity. So you see that instead of the vorticity being concentrated into vortex, it just sort of spreads it into.
Vorticity is conserved because it's 2D.
Ah, that's a good question. Yes, this is 2D, so I guess it is conserved because of that.
But dust is a dissipated fluid. Somehow it dissipates the. What is it dissipating? Okay, sorry, I'll let you. It just sounds. Yes, I don't understand this.
Yeah. So yeah, I actually never wrote out the vorticity equation with dust reaction included. So
okay, we see what you get.
I am not sure if it has a term in the vorticity equation, but you have to see.
Okay.
So given all of that, let's run some simulations and see what happens. So I'm going to stick in 2 planets at 1 and 2 AU. The planets have masses of 21 Earth masses. In case you wonder why such an odd number, these are planets with 0.5 thermal masses. If you don't know what the thermal mass is, that's okay, not too important. The dust will have Stokes number of 0.01, and the dust to gas ratio is also 0.01. And these are the parameters for the disk. I'm going to show you an isothermal simulation and a simulation of the cooling time that is 10 dynamical time.
Can you modify the code to put in more than one size of dust grain?
Yes.
Okay, so that doesn't, it's not a problem.
Yeah,
does it slow things down? You have to have more fluids, or?
It slows things down in the sense that you just have to simulate an extra fluid.
Yeah, okay.
Yeah. If the dust have to interact between species, then that would be a different story. So if the dust doesn't have to interact with each other, then they all just interact with the gas, then it's very straightforward. So this is what happens if you run an isothermal simulation of 2 planets. So this is isothermal. There is dust, but the dust is not back reacting on the gas. This goes to about 50 kilo a year, 50,000 orbits. And you end up with two planets in here, 2 gaps, and 2 rings. You can already see in the gas, it's not as extreme, but in the gas you can see a vortex over here. There is actually a vortex in a lot of other places too. In the gas, it's not obvious, but in the gas you can immediately tell. This thing is an arc. There's a vortex here. The density contrast is orders of magnitude. So in ARMA, you would not see this as a ring. And then you have cooling plus dust feedback, then the picture becomes a lot more boring. You just have rings. It's a bunch of rings being there, and they are just there. So if you're interested in the speed of the code, this all runs on a single GPU. 50,000 orbits in one, took about 1 day.
Quick question.
Yes.
So do you have to fine tune the cooling time as well as the stopping time to get this result, or is it pretty natural?
I didn't, although in the way of testing, when I was running my code many times on different settings, I've tried cooling time of 10 or 100. After long enough time, it just looks the same. So I think the cooling rate is not such a strong function for not crazy choices of cooling time. But of course, you can think maybe cooling time is extremely long, maybe like 1,000, 10,000 orbits. Then I'm not sure.
So the cooling time is through radiation is what you're trying to model? In other words,
yeah, so right now there's no radiation model in any way. It's just this cooling time stuck into the code.
Okay.
So
So it might depend on if you're irradiated as well, right?
yes. So real hydrodynamics, thermodynamics would give you some more physical results. But the point here is that any sort of cooling will try to kill the vortex.
Right.
So here is just again reiterating the message. You have isothermal ended up with arcs, vortices, clumps, and then you add cooling, then you get weakened vortices, and you add dust feedback to cooling. Yeah, just end up with rings that's not too different from what you've seen. And all of this is done without any viscosity. So no need to add any artificial viscosity, no need to add friction. You can make rings. That's it.
So the main point, sorry, the main
Yeah.
point is the cooling. That's a pretty picture. Is a swimming pool?
Cooling.
Is cooling the key process here in destroying the non-AC symmetric?
Yeah, so cooling and dust feedback is hard to compare the two. I haven't done the study yet. So the two have their own favorite parameter space. Cooling is best if cooling time and turnover time are similar. Dust feedback is best if you have a lot of dust and the Stokes number is about 1. So I think each of them will play a different role in different parameter space.
So can I ask, dust feedback, you just mean the sort of extra force on the gas from the dust?
Exactly. It's just that.
Okay.
Yeah.
Okay.
Nothing.
It's a little bit of friction.
It's like a friction, yeah, exactly. But it's
It's
and it's only
pointed
felt
towards
because
pointed towards the pressure max inside the vortex, right? Because dust wants to go to the pressure max inside the vortex.
Yes.
And that pulls the gas out because it's the momentum conservation.
It sounds like it has to, yeah.
That's similar to what I imagined, but I think maybe a true analysis of that, you have to look at the vorticity equation and see what term the dust feedback produces.
Well, if you want to pull the dust inward, then you have to push the gas out.
Outward, yeah, exactly. In
order to question, why are you convinced that the outer parts of protoplanetary disks are essentially inviscid?
So viscosity, if you think of viscosity as what normally you would think of in physics, then like what is the amount of friction in those gases? You can think of it in terms of the molecular viscosity. So that's basically alpha would be something like the mean free path divided by h.
Oh, sure. You know,
right. So that's tiny.
Kinetic viscosity is tiny.
Yeah. So that's number one. I think that's already a fairly important point because viscosity and turbulence are almost the opposite in real fluid. A turbulent fluid is probably low viscosity, and a highly viscous fluid is probably laminar. Yeah. So they behave differently dynamically. Yeah. The only similarity between them is globally they produce similar diffusion. So that's already I think important. And then in terms of amount of turbulence, I'm pretty agnostic about that. I just look at the observations and they tell me the gas seems pretty laminar. So,
but all these observers are incredibly dusty. So if anything, they should soak up the electrons more than other disks. So it's more unlikely to have MRI.
Well, no. I mean, the particles are large, and we really.
But no, we see small grains. We see rich abundance of small grains because they scatter starlight. And they even seeing PAHs, and PAHs are very good absorbing electrons.
It's a little different. I mean, the scattered light you're going to see from the top of the disk. It's not so clear that you're going to see anything in the midplane of the disk. But, small grains.
But the top of the disk is where the cosmic ray hits, right?
You don't need much dust to produce scattered light.
Yeah.
Right.
No, I agree, but these are really massive disks. So if you just take a minimal mass solar nebula, the dust is already, and take some normal dust distribution, is already getting marginal. And these are really dust-rich disks. And I think
so they've got gas masses too for a lot. These are these are all ALMA images, right? So they must have gas masses, estimates at least from these, right?
CO.
CO, exactly. Do you know, are they pretty massive?
CO has been shown to be underbounded. Yeah, the
Sure.
gas mass is
Sure.
also, yeah, gas mass turned out obviously very high too. And some of them close to gravitational unstable. But the CO mass is a bit messy. That's a different story.
No, I'm well aware of problems, but I mean, it'll give you, like you just say, a lower limit, for example, right? You could just take the normal alpha CO and get a limit. But you're claiming that these disks that Jeff is showing here are getting up towards Q equals 1.
Dust mass is huge.
Well, how about the gas mass, though? I mean, the dust mass.
I think my impression was that the gas mass is still pretty ambiguous.
Yeah, so a lot of this don't have very good CO detection.
Right. But dust mass is what matters, right?
Yeah,
dust mass is
but they have the dust mass. So usually the gas mass that you see reported is just that multiplied by 100.
And this is continuum at a few, like a millimeter, a bit longer. So you're going to see, well, it is bigger grains you're going to be sensitive to, right?
The thing is, if most of the solid mass is in millimeter-sized particles and it's more dilute, has a lower density than the inner disk, then ionization effects are going to be enhanced for both reasons. You know, ionization effects due to external ionization, the UV, the cosmic rays, are going to be enhanced if binary collisions in the disk are suppressed due to the low density and due to the greater transmission.
No, I agree. I think the juries
and due to the reduced surface area. So if there's any part of a protoplanetary disk that's going to be significantly ionized, it's going to be the outer parts.
Outer parts more likely ionized. I agree. But there's so many uncertainties. And what Jeffrey's pointed out, there's this turbulence measurement. Sounds the turbulence measurement.
There is no turbulence.
And there's no turbulence. There's also the scale height measurement of large grains. That's the HL tau case.
Yeah.
That's few cases where we actually have very good constraint. Doesn't look like there's much of a turbulence.
Right.
So we're going off of Jeffrey's topic, which I think was a great talk, by the way. But for these stars, you probably can't see the star. You can't get spectra, so you can't say anything about what the accretion rate onto the star is. I mean, that's, it's the inner part versus the outer part. But are there any estimates of that, Jeffrey?
I think a few, maybe not all of them, but a few of them have measurements. I don't remember any numbers that are out of the ordinary.
They're all HL taus. I mean,
they're like 10
all T-Tauri. They're all T-Tauri stars.
They're all sort of 10 to the -8 or whatever the magic number is.
Something between -10 to -7, something.
Yeah, exactly. Okay, and so even at 10 to the -8, then you can work out effectively what alpha is, right?
You can, yeah, of course.
Yeah, and it's sort of the numbers you were talking about, that it's below 10 to the -3 anyway.
I think if you work out the alpha that way, I don't remember if anyone did it and show the number, but I think if you do it, you probably get a pretty typical number too. So an alpha that may be 10 to the -3, 10 to the -2. It's just that people are talking about various ways of driving accretion without turbulence. So, for example, surface layer accretion, range-driven accretion,
right.
Or just other ways of pushing gas inwards, like having a planet in there.
Well, that's a really interesting question. Yeah.
Sorry to interrupt really quick, but Jeffrey, are you done with your talk? Like I'm told, we're cutting into the. Yeah. So we have a 2-hour discussion, so it's totally cool to keep on talking exactly like we were. It's just I want to make sure that people who want to leave can, and I'm very much staying for the discussion as well. But yeah.
Okay, so just as JJ already said, I'm going to Clemson, and so if there's any student in the audience who are looking to do graduate work in this kind of field, I'll be there. So look it up. That's it.
Okay, hi Jeffrey. I have a question regarding the variety of disks that we just discussed. If we don't know the dust to gas ratio so well, then there are other things that can produce similar morphologies. So there are radiation pressure can induce structure. And also there could be, with less gas than dust, there could be avalanches. But dust avalanches don't look like an avalanche. They don't look like radial features.
Mm-hmm.
They actually look like these arcs or blobs.
Mm-hmm.
So it's a little bit confusing. It's very interesting. There are so many ways of introducing structure into the disks.
Yeah.
But have you thought of including radiation pressure? That's the first question. And the other is it very difficult to have really many bins of sizes and interaction between those bins via collisions, which would be necessary to study the avalanches?
So first of all, it would be very difficult to include many bins. I think it would. The number of bins that you include would just scale proportionally to how much longer the simulation is going to take. So yeah, if you want to have 1,000 different species of different masses, that's going to be very expensive to do. And then the fluid approximation is probably not the best way to do it anyway, because you have particles that are trying to cross orbit.